This presentation is about Service Fabric, a distributed platform for building microservices in the cloud. My name is Kevin Jingqiu, and I will be presenting this paper. So we'll start with a short introduction, and then we dive into the core components of Service Fabric. After that, I'll present some of the findings in evaluating Service Fabric, and finally offer a little critique of the paper. Introduction. So what is Service Fabric? Service Fabric is a platform for building microservices in the cloud. And what does microservices for the cloud mean specifically? According to the authors, that means the services must be self-healing, self-adjusting, and self-sufficient. That means built-in fault tolerance, easy scalability, and no dependency on external systems or storage. Moreover, the platform also provides strong consistency and support for stateful services, so application developers can rely on it to implement reliable, persistent, efficient, and transactional data services. And how does Service Fabric achieve all of this? And that's the topic we're going to talk about next, the architecture and key components of Service Fabric. Conceptually, Service Fabric is a multi-tiered system with the federation subsystem at the bottom. This subsystem provides critical distributed system features such as failure detection, consistent ring with routing, and leader election. Built on top of that is the reliability subsystem. This layer provides replication and high availability through components like the failover manager and the PLB, which is placement and load balancer. And the reliability subsystem allows the creation of the reliable collection, which is an abstraction for distributed storage. Now let's take a look at each subsystem in more detail. First, the federation subsystem. As alluded to before, the role of the federation subsystem is to provide consistent membership, failure detection, routing, and leader election. In Service Fabric, nodes are laid out in a virtual ring like this. Each node keeps a list of its direct successors and predecessors. And this is called a neighborhood. Neighborhood is used as monitors for that node. So first, a node periodically sends its heartbeat in a message called a lease request to its monitors. If everything goes well, all the monitors will send the node a lease request acknowledge message with a lease period TM, which is normally 30 seconds. This basically says that the monitor promised that it will not mark the node as failed for at least 30 seconds. If the node receives acknowledged message from all of its monitors, it stays in the membership list. Service Fabric is designed to be strongly consistent, so if the node fails to get acknowledgement from all of its monitors, it's considered to be removed from the membership list. I say considered because the final decision is not made by the monitors or the node itself, but a separate process called arbitrator. Unlike other failure detection protocol, which allows for inconsistent membership lists, Service Fabric uses arbitrator to decouple failure detection from decision so that a consistent membership list can be maintained, and it allows for high scale at the same time. In our example, the monitor detects the node as failed, so it sends a failed message to the arbitrator group. If the arbitrator group already has that node as failed, then it ignores that message and asks that node to leave again. If this is the first time that the node is detected as failed, then the node is added to the recently failed list, and the arbitrator group sends a message accept back to the monitor, and the monitor waits for a timeout T of O before taking action to claim the portion of the ring that was previously occupied by the failed node. Here are some key takeaways for the failure detector in Service Fabric. First, the membership list is strongly consistent among all nodes, and failure detection is decoupled from failure decision through arbitrator nodes. We covered failure detection. Let's move on to how routing works within the Service Fabric platform. To understand routing, we have to go back and look at the ring topology. For a ring with m equals to 8, the key space is from 0 to 255. Each node is assigned node ID and is responsible for the keys with IDs lower than the node's ID but greater than the node's immediate predecessor. So let's look at an example. Take node 64, for example, the green node down here. It's responsible for keys with ID from 50 to 64. Because 50 is the node ID of immediate predecessor. Each node has a routing table which is generated using the formula ID plus 2 to the ith power mod m to the mth power, with I being between 0 to m minus 1, which is 7 in this example. When a request with a key ID of 236 comes in to node 64, the request gets routed to the node that's closest to 236. That node 64 knows of. In this case, it's 200. The request goes to 200. And from node 200, it looks up its own routing table and finds node 225 being the node that's closest to the key 236, and hence it routes that request there. And because node 225 is responsible for the key range between 225 and 250, the key 236 fits in that range. So node 225 is the final hop of this route, and hence the routing is finished at this node. At first glance, this system is very similar to the Chord distributed hash table. Just like Chord, routing tables are eventually consistent. However, there are a few key differences. The first difference is that Service Fabric routing table entries are bidirectional and symmetric, whereas Chord is not. This speeds up the dissemination of information as well as routing, which makes Service Fabric more efficient. And unlike Chord in other distributed hash tables, Service Fabric uses a host of information to decide which keys should be mapped to which node. For example, the nodes in the neighborhood are selected from different failure domains, so that improves the fault tolerance of the ring. The last major component of the federation subsystem is leader election. Leader election in Service Fabric is built on top of the previous primitives, such as ring, routing, consistent neighborhood, and every key k in the ring has a unique leader, which is the node whose token range contains k. Therefore, leader election is implicit. This concludes the discussion of the federation system, and we'll move on to the reliability subsystem. Just to remind you where we are, the reliability subsystem is in charge of replication, load balancing, and high availability. There are a couple of major components of the system, and we'll be focusing on FM and PLB, which stand for Failover Manager and Placement and Load Balancer. Here's how they work in tandem. There are nodes in the Service Fabric ring and services running on these nodes. Each node has a daemon process called reconfiguration agent. The job of these reconfiguration agent is to collect node status, such as available memory, CPU usage, disk space, network accessing pattern, etc. and the usage reports are sent periodically to a replicated service called the failover manager. The failover manager aggregates these reports and sends them over to the placement and load balancer, the PLB. The PLB looks at the reports, figures out the optimal place for the services to run, and tells the failover manager to reconfigure or to move a service replica to another node. For example, if node 3 is running out of resource and node 5 and service 5 is suffering because of it, and the PLB sees that node 2 has extra room, so it tells the failover manager to move node service 5 from node 3 to node 2. The metrics the PLB uses to make balancing decisions include node stats like CPU, RAM, disk, conceptual resources such as number of requests on the service, or the parameters of a typical request such as request size, frequency, etc. And finally, the failover managers themselves might fail. To mitigate that, a failover manager master is elected to handle failures in the group using the exact same logic as the failover managers themselves for managing the microservices. If the master dies, a new master is elected and it reconstructs its state by querying the ring. Finally, the top layer of service fabric is called the reliable collections. And just to remind you where we are, that's the top layer. Reliable collections provide stateful services in service fabric. For example, the reliable dictionary and reliable queue. It's highly available and fault tolerant via replication. It's persisted via disks so that it can withstand outages. It's efficient via asynchronous API that do not block on I/O. And it's transactional via APIs with ACID semantics. And the key takeaway here is developers only have to deal with reliable collection APIs. They do not need to worry about consistency because it's assured by the lower layer components. Now let's look at some key results of Service Fabric. One of the novel ideas in Service Fabric is decoupling failure detection from decision using an arbitrator. In this paper, the researchers have presented some data points with regard to the benefits of using an arbitrator. In this chart, they measured the number of nodes leaving the ring with different failure detectors. The black bar here is the one with arbitrator, and the other bars are without, with varying number of monitor nodes. As the chart demonstrates, the arbitrator has far fewer nodes leaving the cluster. This is mainly due to the fact that arbitrator-less scheme has a cascading effect on failures. Next, they also measured the overhead of the failure detector in Service Fabric. In this chart, the y-axis here is the messages per second in the entire system, and the x-axis is the number of nodes in the ring. The three different colors represent the different number of monitors in the ring. As you can see, the overhead scales linearly with the number of nodes, which means the per node overhead is a constant. And finally, the routing mechanism in Service Fabric is an improved version of the one used in Chord. The researchers also published a chart comparing the effectiveness of the routing mechanism between the two. As you can see in this graph, the median number of hops in Service Fabric sits below that of Chord, with the 99th percentile number of hops far fewer than Chord as the number of nodes in the ring increases, meaning Service Fabric routing is much more efficient than Chord due to its bidirectionality and symmetry. Finally, I'll offer my brief critique of this paper. Just a disclaimer, I'm a student of distributed systems, but I'm by no means an expert. First of all, Structurally, I feel the paper spent too much time talking about microservices and its benefits and repeated itself a couple of times in a few different sections. I feel this space could have been better served by talking about Service Fabric in detail, for example, providing a small but concrete example on how to utilize it for building applications. And second, some details are left unanswered. For example, how does the arbitrator group detect failures among itself? How does the ring know its liveness condition is satisfied during routing? And how is the state reconstructed from the ring to recover from failover manager master failure? And lastly, security is a key aspect of the system that was not covered at all. For example, how do nodes in the ring identify each other and make sure they are who they say they are? Is it through mutual TLS with in-cluster certificate authority or something else? How are the messages exchanged between the nodes? How are they secured during transit? How are secrets stored at rest? What are some of the potential attack vectors? And what about Byzantine failure scenario where bad actors in the cluster can alter the messages? Questions like these are important for a platform that's critical business applications are built upon. Okay, that concludes my presentation on this paper. I thoroughly enjoyed reading about Service Fabric, and I hope you have learned something as well. Thank you.